we're going to, by the way, today is the 21st, so it is January 21st, 2016. This is our Thursday lecture. And we kind of ended with all this stuff on the board, and I wanted to just add a few more details to what we ended with last Tuesday, and just kind of show you what the integration limits might be if, for example, you have electrons going around a lithium nucleus. So in spherical polar coordinates, it'd be R1 would go from 0 to infinity, and theta 1 would go from 0 to pi radians, and phi 1 would go from 0 to 2 pi radians. And similarly, for the second electron, R2 would go from 0 to infinity in meters if it were SI. Theta 2 would go from 0 to pi radians, and phi 2 would go from 0 to 2 pi radians. And now we'll ask the students in the class to do the third one. So R is going to go, this is the coordinate for our third electron. It goes from where to where?
0.
0.
2 radians. Or, sorry, infinity.
Yeah, in principle, that electron could be right next to the nucleus to 1 billion light years away.
Yep.
Okay, and now what about our angles? Theta 3 can go from
0 to pi.
0 to pi radians.
2 pi.
And phi 3 would go 0 to 2 pi radians. So I just wanted, while this was on the board from Tuesday's lecture, to kind of remind you of all the limits, okay? Now, what is psi star psi itself? This whole thing, from this to the other, is the probability finding the 3 electrons between all these R's and all these thetas and all these phi's, plus little increments and all this. And just the wave function complex conjugate, which we indicate by star, times the wave function, that is going to be the probability per unit angular and radial distances that are covered in this differential element, which has dr, d theta, d phi for particles 1, 2, and 3. We ended up erasing this last one. Let me write it. So this is dr3, d theta 3, d phi 3. All right. So now let's erase the board and move on. Let me again, while I'm erasing the board, draw your attention to the checklist of key equations on page 280. We're going to be using those equations in the brand new chapter that we're going to be starting today in just a few minutes. And that is listed right there at the top of our board, where you want to know. Now, I want to mention just very briefly right now, we'll come back to it in more detail. We want to talk about Heisenberg's uncertainty principle. Now, do you remember who Heisenberg was? What was he doing politically and scientifically in the Second World War?
Well, he was trying to. Hitler wanted him to try to be part of his nuclear program.
So yeah, he was in charge of the German atomic bomb effort,
Mm-hmm.
And there are speculation.
And he
that
also put together a wave function equation involving matrices.
Exactly right. The thing for which he's obviously a Nobel Prize winner in physics, the thing for which he is most famous scientifically, and rightly so, is the uncertainty principle. And the key idea, which has been taken up by theologians and philosophers, is that it's one of the major ideas of the 21st century. The key idea is measurement perturbs what is being measured. Thus, introducing uncertainties. And let me just note that this idea is important particularly important for small objects. Atoms, molecules, and subatomic particles. We could probably put a measuring tape or a laser onto an automobile or even a Major League Baseball's home run, and we wouldn't perturb it all that much. But when you start figuring out what's going on with things the size of atoms or molecules, particularly subatomic particles like electrons, protons, and all that zoo of subatomic particles, this can become very significant. Now, the classic form of the uncertainty principle is with respect to position and momentum. So these are the uncertainties in position and momentum. And we just without proof or explanation, we just kind of want to write down what's going on. And let me just check on our book's notation. I'm actually looking on page 280 of our text. So this is the position, momentum, uncertainty principle. And let's just look at some of the mathematical consequences of the uncertainty principle for position, momentum. And there's many other ways with many other variables to express the uncertainty principle. So if the uncertainty in momentum is small, the uncertainty in position has to be larger. So it's just algebra, isn't it? Let's go to the equality, not the inequality, but the equality says if you have a small delta p, you have to have a larger delta x for their product to equal h bar divided by 2. So you really get the momentum precisely, you don't know where the particle is position-wise. The other limit is you say, okay, I want the uncertainty and the position to be small. I want to know exactly where it is. the uncertainty and the momentum therefore becomes larger. So if I really try to tightly define one of these, have the uncertainty be very, very narrow, the uncertainty in the other quantity grows.
It's weird.
Okay? You know, that it's weird, it's profound. It is not only a key idea of physics, but as we mentioned, of philosophy and theology. They've really grappled with the uncertainty principle. Now, we'll have a lot more to say about how you calculate delta X and delta P in the uncertainty principle. That's coming. I don't want to do it right now. I just wanted to introduce the uncertainty principle at this point. And again, there are many manifestations of it, of which this is just one. It's the historically most famous, and it's still a very significant form. Okay. Let's now move to the new chapter. And in particular, we are going to move to particle in a box. And we're going to start seeing the full manifestation of quantum theory. Now, for you in this class, you've already seen this. We had 3 carbocyanine dyes with varying alternating hydrocarbon chain lengths, conjugated lengths. And we saw as we lengthen the chain, therefore increase the width of the length of the one-dimensional box, we saw that the energy levels changed. And we now kind of want to develop a theory that goes along with that first P-Chem lab that we have done. Okay, so we're into chapter 8. So we're continuing our journey in quantum mechanics, and we're going to look at various mathematical techniques and how to apply them. Techniques and applications. We laid the whole theoretical groundwork. Actually, our book does a very good job of that in chapter 7. Now we're going to go to specific systems. We're going to look at examples of what's going on. So we want to look at 2 example systems as we begin this chapter. One, a free particle in one dimension. And particle in a box in one dimension. If you properly understand these 2 cases, they provide the essential insight as to what's going on in quantum mechanics. And from these, we can readily generalize to the kinds of atomic and molecular systems that will direct our attention through the rest of the course. So, do you have your book with you right now?
Technically, I do, yeah.
Okay, why don't I just share
it's
with
in
you.
I have a hard copy I don't have with me, but I also have a book that's on my computer.
let's just work from my hard copy.
Okay.
Okay. So a specific example of a free particle in one dimension would be an electron that moves only in the x direction. And there are no barriers, there's nothing there. It could just go in one, it could go in 3 dimensions, but to make things simpler, it's just a free electron. You can just imagine it could go this way or this way.
Mm-hmm.
There's no boundaries, no barriers, no nothing. Okay. We might envision a highly conductive thin wire of infinite length, and the electron could be anywhere in that wire. It can freely move between plus and minus infinity, or 0 to infinity. Would probably be a better way to look at it. All right. Actually, probably minus infinity and plus infinity would be better, but let's think of that case. And we talked a little bit about it last week. The Hamiltonian operator, h of x, for this system is the combination of the kinetic energy operator, t of x, plus v of x, the potential energy operator. What do the hats indicate? Let's make sure we remember that.
The hats indicate an operator.
Exactly. Now, if this electron is freely moving in one direction, there's no magnetic fields, there's no electric fields, the electron doesn't feel the nucleus of all the metal atoms in the wire.
0 potential energy.
So there's absolutely 0 potential energy. And so our kinetic energy formula is minus h bar squared over twice the mass of our particle, and we'll take the second derivative with respect to position. The curvature of the wave gives, the matter wave gives the position. So Schrodinger's equation looks like this. Minus h bar squared divided by 2m, second derivative with respect to x of our wave function equals the energy of our wave function back again, times our wave function back again. So that's Schrodinger's equation for a free particle. And we mentioned briefly last time that the solutions can be functions of k. They can be psi of k. They are of the form a e to the I kx plus b e to the minus I kx. They can be of that form. And if you substitute in, and we've actually done this, if you'll recall, we've actually worked through this case. So
Yeah.
I just want to give the key results, that the resultant energy is a function of this wave vector k equals k squared h bar squared over 2m. and you can have any value of k. Therefore, any value of E. You can have any energy you want, you can have any K you want. You're free, under no obligation, under no restriction. You could also have, you could also set this up, by the way, as psi K equals C cosine Kx plus D sine Kx. And do you recall why these two functional forms, either the e to the plus or minus ikx, or cosine kx or sine k, why those particular functions?
Because the derivative of them is the same.
Within some constants, which come out.
It doesn't really change.
That you take two derivatives of the cosine, a first and a second, you'll get cosine kx back plus a k squared, it'll be a minus k squared.
Yeah.
If you take two derivatives of this, you'll get a minus k squared.
But what's important? What's staying? What's not changing?
The e to the ikx isn't changing,
E to the ikx
or the
isn't
cosine kx isn't changing.
Yeah.
And you get a k squared out and you get a sign change. The sign change is handled by that sign change in front of the operator. Okay? And you're proving that the second derivative of the function equals a k squared times the function. And when we solve, we'll get k squared h bar squared over 2m.
Mm-hmm.
Okay, simple as can be. Okay, we've already kind of gone over that, and this is the free particle in one-dimensional problem, okay? This particle can go from plus infinity to minus infinity if we want to do it that way, okay? Now, here's something brand new. What if I confine the particle to a wire length L? So now all of quantum mechanics is going to fall out into our lap right here. Absolutely incredible. So we have a wire of length L. The electron is free to move on x-axis between 0 and L. And so between 0 and L, v of x equals 0. Just like what we have over here. The potential energy operator is 0. Free within, as long as it stays on the wire. Can't jump off the wire. Now, if x is less than 0, but if x is less than 0, or x is greater than L, what is v of x?
So if x
Is less than 0 or greater than L.
If x is less than 0 or greater than L, then we have only negative.
Now, imagine a jail that consists of a well with smooth, unclimbable walls that's however many feet deep. Okay? Now, if you were encased in a concrete tube that was up to your neck, you could grab with your hands and get out. But if it were 100 meters tall, and it wasn't big enough to shinny it, you know, and you had no ropes or tool, you couldn't get out of there and be as good as between bars. Okay. You remember the well story where, you know, they put him in the well in the Bible and they can't get out.
Yep.
Okay. So, for all practical purposes, this potential energy is infinite. The electron can't easily jump off the wire. It's going to stay on the wire unless you have something like a Tesla coil with literally thousands of volts, which approximates infinite energy. Okay. Now, if the potential is infinite, the wave function, which is probability of being there, it says you can't get out.
Why is it less than 0 though?
Oh, it's just position. In other words, it could go to minus infinity.
That's it, just minus infinity.
Yeah. X is what? It's between 0 and minus infinity. So.
Yeah, I get that. I just don't understand why is it because it's greater than L though? That's why the potential energy is infinite?
I'm saying we have a length of wire, L.
Mm-hmm.
Starts at 0, ends at L. Electron can freely move on that wire, but it can't jump off the wire.
Yep.
Okay. And this is between 0 and minus infinity for x less than 0, and between x and plus infinity on this side. Okay. Now, what this means is in this region, what is the wave function going to equal? If you can't get out of the well, is there any probability of you being out of the well?
No.
No. And wave function squared is a probability, so in this region the wave function has to go to 0. If you have infinite potential, the wave function, there's not enough energy to overcome infinity. Therefore, you can't be there.
So there is no wave.
It's a maximum security prison. You can't get out. You can't get off the wire. The wave function goes to 0 because the wave function squared is probability, and there's 0 probability of getting outside the well. Okay.
Mm-hmm.
Now let's look at this. Minus h bar squared over 2m psi equals, now let's just solve this equation. Minus, oh, I have to get the second derivatives in there. D squared psi dx squared. Now, how do you solve that? You're saying the curvature of the wave function equal, the second derivative equals infinity. Now, there's a real clever way to do this, okay? This side of the equation is infinity, right?
Mm-hmm.
This is just a curvature. The elegant way to solve this equation is to say Schrodinger's equation is solved if, so this is outside the box. Schrodinger's equation is solved if psi of x equals 0 or x less than 0 or x greater than L. Because if this is 0, the equation is solved. 0 equals 0. In other words, mathematically it says that wave function has to go to 0. Mm-hmm. Intuitively it says that has to go to 0. It's all in the box. Now we're ready to do what's in our course. So I can safely neglect what's outside this 0 to L region, because the wave function goes to 0, There's no point in being there because I can't be there, because it says there's no probability of being there because I can't get out of the well. Okay?
So it's a node. No, I don't know.
Okay, now. All right, now we come to another exciting development, okay? So now we're in the well, okay?
Mm-hmm.
Between L and 0. Our quantum mechanics says minus h bar squared over 2m psi of x equals E psi of x. There's no potential energy in the well, right? Let's just remind her, the V of x equals 0 in the well. So the Schrödinger's equation is just like what we wrote for the free particle.
Mm-hmm.
Now, what are the free particle wave functions? Well, they're ones that do this. And in the well, they're going to have the form A e to the ikx plus b e to the minus ikx. Or if you want to do sines and cosines, that's fine too. Let me get, I just want to harmonize my notation with theirs. I think I was backwards. They have c sine kx plus d cosine kx. I think I wrote it the other way if you look back in the notes. Like I think I associated c with the cosine and d with the sine.
Yeah.
Okay, it
It's
doesn't
all right.
matter.
Yeah, I wasn't thinking it doesn't matter.
It doesn't matter. Okay, the book does it this way. So we can either have the complex e to the power, or we can have sines and cosines. And as we mentioned, these have the unique property that it's constants time. The second derivative gives the wave function back again times some constants. All right. Now. We know what our energy is. Okay. Let me write it again. It's E of K. The quantum energies, which we can readily solve and prove for, are K squared H bar squared over 2m. The wave functions have these properties. Okay? Now, in the free particle, we had no restrictions.
Mm-hmm.
But now, pay close attention to what we are about to do. We're going to look at boundary conditions. What does that mean? It means that at psi of k equals 0, the wave function has to go to 0.
Yep.
We're at the edge of the box. There's no probability of getting out. The wave function there has to have 0 magnitude. And we have to have psi k of L is also 0. Those are our boundary conditions. It just says the wave function has to go to 0 when we encounter that infinite potential barrier at the edge of the box. Okay? Now, let's simply substitute the trigonometric form, the lower of the two forms, in here and see what conditions those put on us. So we can say, well, that's just C. So I'm going to do the 0 one first. C sine of 0 plus D cosine of 0. Right?
Mm-hmm.
Now, what's the sine of 0?
0.
Okay, so this whole term goes to 0.
And you have 1.
This term goes to 1.
Or D.
And if you want that to go to 0, you only have one choice. D has to be equal to 0. You can't have the cosines, neener. You got the 0 boundary, it says no cosines. Because the wave function doesn't go to 0. The sine's fine. Okay, now we go to the L value. So we threw out all the cosines.
Okay.
Okay, and we can do a similar thing with this function up here. What about the L boundary? We can say, okay, all we have are sines, so it's C sine KL has to equal 0. Okay, when is the sine 0? The sine is 1 at pi over 2.
Oh, sorry. Sine 0 is 0.
0 at 180 degrees.
Pi.
Okay. Okay. So KL
Has to equal to 0 or pi?
has to equal n pi, where n can be 0, 1.
And we're
2.
still, you're just showing me different examples of boundary conditions, yeah?
These are the boundary conditions for an electron on a wire.
Okay.
It can't go off either end of the wire.
Mm-hmm.
Okay. So to get this condition, this is how boundary condition is satisfied. You say KL has to equal an integer number of pi radians, where n can go 1, 2, 3, 4, and so on. In fact, it could even be 0, right?
Yep.
Because the sine of 0 is 0. The sine of pi is 0. The sine of 2 pi is 0. The sine of 3 pi is 0. So KL equals n pi. And we can readily solve this. We can say, well then K has to equal n pi divided by L. So we have, and I want you to appreciate this, there are now restrictions on K. It can't be anything it wanted to be, like in the case of a free particle. But now it can only take on the values n pi over L. Quantum energies. Only certain energies are allowed. And can we find what those energies are? You bet. We can go right into here and substitute this quantum condition. And now the energies become E sub n's. And let's put k squared in there. Pi squared over L squared h bar squared over 2m. See if I got it all in there. In the numerator, an n squared and a pi squared, I got it there. In the denominator, an L squared, and then h bar squared over 2m. So these are the quantum energy levels. Particle in a box. And again, n can take on the values at this point 0, 1, 2, 3, 4. Okay. So now all of quantum mechanics, as classic non-relativistic quantum mechanics, if you understand this problem, you understand it all. Because we restricted the region that the electron could be in, and that led directly to boundary conditions, because the wave function has to go to 0 at the boundary and beyond the boundary. And at the boundary, we threw away all our cosines, and we had a form constraint, and we also have an energy constraint, Ek, now goes to En, n squared pi squared h pi squared over L squared times 2m.
So basically n pi over L
Goes now into the sine function.
which is basically, it holds a constraint saying that only specific levels are allowed in particles.
And only specific types of matter waves are allowed that go with those.
And it's dependent, or it's dependent on the length though, so you could open it up double and then two different.
That's right, and the quantum energy levels change, and that's what we were doing in lab by lengthening the conjugated chain of those polymethine dyes.
Mm-hmm.
Imagine the electrons in the dyes can move freely from one end of the chain to the other. We are just putting more and more conjugated hydrocarbons, and we are shifting the spectrum. Now we need to normalize particle in a box. Wave functions.
So if you make a box a specific length, basically some will work and some won't.
If you make a box a specific length, that will affect the allowed quantum energy levels.
Okay.
In fact, the bigger the box, the more closely spaced the energy levels, the tinier the gap between them.
Okay.
Okay. Now, the normalization says let's let x go from 0 to L, and we're going to do psi n of x star psi n of x dx has to equal 1. That's the rule, right, for normalization. The total probability of finding that electron is somewhere between 0 and L. Okay, now I'm going to erase this board. And we're going to put in the actual values of the wave function that we get. So this is the integral from x equals 0 to L of c sine n pi x over L times c at that star c sine n pi x over L once again dx all has to equal 1. Now, this is what we call a real wave function. It doesn't have any complex numbers in it. So in this particular case, we have x equals 0 to L of c squared sine squared n pi x over L dx has to equal 1. Okay? Now, pull the c squared out. That's our normalization constant. X equals 0 to L of sine squared n pi x over L dx. This is an integral, a common integral. You can do it yourself, or you might want to look at some of the common integrals that you'll find in this course. So in the front cover of your book, there's an integral for sine squared ax dx.
Yeah.
Okay? And my daughter, Celeste, is taking calculus in high school, and they're making her do the limit form before they unleash the calculus.
Yeah.
And she, I know how to do those, why do I have to do the limits? And this is crazy. So she's, little pity and whining, that she's doing. Well, we're taking it one step further. We're not even going to do the fancy method. We're just going to look the darn integral up. And we're not going to be ashamed. We know how to do integration by parts and all this trigonometric stuff. But we want to do physical chemistry. We don't want to do integrals. We're going to look the integral up, which is conveniently provided in the front cover of our book. Thank you very much. So we learn that the integral in the front cover of the book, the quantity n pi over L is their A. So integral in the book. So keeping to that definition, we'll put everything in and we'll see what we get. So we're going to get, let me make sure I'm doing the right integral, 1/2 x minus 1 over 4a times, let's see, minus 1 sine 2ax. Let me see if I've gotten that 1 over 4. Okay, I've got it. And this is evaluated between L and 0. Now, immediately, we can see that the 0 limit is going to go away because the x term will go away and sine of 0 is 0. So if we can evaluate the L limit, we've got it. Okay? So this is 1/2 L minus 1/4 A sine 2AL minus 0 minus 0. So I did the L limit minus the 0 limit is that. Okay. So now let's keep this 1/2 L in mind here, and now we have to put in what the A is, and the A in our case, by definition, is n pi over L. And convince yourself that the argument of this is 2n pi, and the L cancels out, and this whole term goes to 0. So what we're left with, if you look at this whole equation, what we're left with is all of this, okay? Let me just, I'm kind of running out of room here. So I did the integral, and strictly speaking, I should have had a c squared in front of this, okay? Equals a c squared in front of this.
Why does sine equal 0 right now?
Why does what equal 0?
You cross the sine out and put 0.
Where?
Right here. You put an arrow.
Oh, okay. I do the L limit, this and this.
Mm-hmm.
Then I put minus the other limit,
Yeah.
minus 1/2 times 0.
Yeah, I'm sorry. I thought that you were crossing out sine, but you're pointing an arrow.
Yeah, I was crossing out sine, but that's on the L side of the limit.
Yeah.
Okay, and then I show that on the other side,
It's just 0. Yeah.
it's all 0.
But why are you crossing out sine on the L side? Why would you?
Because on the L side, A equals n pi over L,
Yeah.
and 2AL times n pi over L gives a result 2n pi,
Yeah.
and it doesn't matter what the L is, that's going to go to 0. Because, look, this is an integer number of pi's.
Oh, so no matter what.
No matter what L is,
2 pi
2n
0.
pi, because n is an integer,
Sine of 2 pi is 0.
that's always going to go to 0.
Okay.
So we have the result. If you factor this all out, it's c squared times 2 over L equals 1, or c squared equals L over 2, or c equals the square root of L over 2. That's the normalization constant of the wave function. So the normalized wave function, psi n of x equals the square root. Now, did I get this wrong? Oh, it should have been. I got this upside down. It's L over 2, not 2 over L.
Okay.
And that, I said, that doesn't look right. Okay. So this, so c squared equals 2 over L, or c equals the square root of 2 over L. These are the normalized particle in a box wave functions. So this step is our normalization step, and we go through all these renditions of this to get this result. Now, there's one last thing that we've got to do before we quit this lecture. And this one's subtle, but it's darned important. Okay. What does the wave function psi n equals 0 of x look like? In other words, or psi 0 of x. What if the quantum number is 0? Well, doesn't that equal the square root of 2 over L
It's just going to be
of
0.
sine of 0, right?
It's just 0.
Which equals 0. Now, there's something wrong with the wave function where the probability psi 0 of x times psi 0 of x dx That's supposed to give you unit probability, right?
Yep.
But both of these are 0. And so this whole integral on the left is 0. Can 0 ever equal 1?
No.
No. So we have to cross out, it meets all the other conditions, but we cannot have 0 probability. And so for particle in a box, quantum numbers start at 1. Because we have to have probability. The wave has to give probability of being there. Now, let's take just a moment to summarize where we've gotten. This is an obvious break point at this point once we finish discussing this. How do we get the boundary conditions? Let's go, there are 3 things that happen to get the boundary conditions, right? Well, 4 if you want to go back and say the second derivative of the function has to give constants times the function. So we have to have this oscillating matter wave, which we can express as e to the ikx, e to the minus ikx, or cosine kx, sine kx. So we have to have that functional form to solve Schrodinger's
You
equation.
have to have a certain length.
And then if we impose a finite length, then we have boundary conditions at x equals 0 and x equal L. X equals 0 throws all the cosines away.
Mm-hmm.
X equals L says, sorry, you can only have certain values of KL, or K equals n pi over L, where n is an integer. Okay? Then we say, okay, that's cool, and we get quantum energies. Then finally we say, but wave functions, particularly when they're normalized, like we normalize, have to give unit probability, and the n equals 0 wave function
Can't work.
has no probability, so the electron is excluded, therefore that's not a valid wave function, and we have to start our numbering at 1, the first quantum length. Now, how does this relate to what you were doing in laboratory last time?
Because we were measuring certain wavelengths, or no, we were going through certain wavelengths through the spectra using the spectrometer, and at some points there was no absorbance at all, but at specific wavelengths there was an absorbance, which is a specific quantum number, kind of what you're trying to say?
Yeah.
Oh yeah, sorry. The 3 different molecules at different
chains,
lengths, or different lengths in their chains.
Alternate,
Allows specific wavelengths.
conjugated, hydrocarbons with effective lengths L1, L2, L3. These are the effective lengths of these conjugated hydrocarbon chains.
Which were, I think, like 8,
And
7,
actually
10.
it was something like that. Our first one was the longest, and we got the chains progressively smaller. So this is like particle in a box, okay? And we have a set of energy levels.
And that's why you had us count the conjugate chain in the beginning.
That's right, because I want to know the relationship between L1, L2, and L3. Okay? So we have all these energy levels. Notice the quantum number starts at 1 because
0.
that 0 is not allowed. Okay, now, in spectroscopy, what do? We start at the bottom of the ladder, and what you were looking at was the E1. I was putting in energy, H nu, or hc over lambda. This is the photon energy. And if that energy equals E2 minus E1, we can get an idea on the relative gaps between E1 and E2. Now notice our formula. So look in your notes and tell me the formula for energy. We derived it right over here.
A squared.
Okay, what was it? Is it n squared? I can look it up on my. It's what we had on the board, just the quantum energy levels of particle in a box. And we can derive them, but we can also look at them. So we've done a nice job getting through the first.
N squared pi squared over L squared. H bar squared.
Okay, so we had, n, okay, so it's n squared, so that's 2 squared, h bar squared, pi squared, over what?
L squared.
Or ml squared, right?
Yeah.
Okay.
Or 2. Did you get, is it 2 N L squared?
It's 2, so the n squared is 2 squared. And then it's minus 1 squared, h bar squared, pi squared, over ml squared. And so this is 2 squared minus 1 squared times the quantity h bar squared pi squared over ml squared. Now notice this energy gap is going to get smaller when L gets bigger. Right?
Yeah.
We're going, let's assume in this case we're going to the second quantum level minus the first. That's the same in every one. That's the lowest one you can do. Okay? But as L gets bigger, everything else is the
Tighter
same.
together.
And the bands are further, the absorption band that corresponds to going from state 1 to state 2. And what the light is doing is converting you from wave function 1 to wave function 2. So you're going from one matter wave to another matter wave of higher energy. And the spectrometer says how much energy you put in through this formula. So in other words, I measure this frequency or this wavelength, and I can tell, and I say, the photon energy has to equal the molecular quantum jump between 1 and 2. And that quantum energy gap is proportional to 1 over L squared. And that's exactly what we saw. The longer the chain, the narrower that gap, and the longer the wavelength.
Yeah.
And we went boom, boom, boom. Now, this is absolutely incredible because we have related what's happening with the spectrophotometer to what's happening with the quantum mechanics. And by changing the chain length L, we change the wavelength or the energy of the light required to go from one wave function to another wave function in a system that models particles on a box. this is absolutely lovely. And this is a perfect stop place for us.
Yeah.
Because we've uncovered the entire edifice of quantum mechanics. We've discovered that quantum conditions come as a result of applying boundaries. And the more we apply, the more restricted we get. We have to pay into attention the Born interpretation of the wave function, that the wave function's probability. That's why we throw out n equals 0. It's why k equals n pi over L, where n is an integer. It's going back and why we threw the cosines out, and going back even further, why sines and cosines and e to the I and e to the minus ik x's work well, because the second derivative of the function equals the function. So really, in simple form, we've covered all of quantum mechanics and all of spectroscopy right here with particle in a box.